Welcome, my friends! Consider the function y is equal to 2 to the x power, which we would like to graph. Let's make a table. If x is equal to 0, then we have y is equal to 2 to the 0 power, which is equal to 1. If x is equal to 1, then y is 2 to the first power, which is 2. If x equals 2, then y equals 2 squared, which is 4. If x equals negative 1, then y equals 2 to the negative first power, which is the same thing as 1/2. If x is equal to negative 2, then y is equal to 2 to the negative second power, which is 1 over 2 squared, or 1 over 4. We can plot all of these points onto the graph, and then connect the dots in a smooth line to draw our function. Note that the line approaches but never reaches the x-axis. This is what we call an asymptote. If we were to make a table for y is equal to 3 to the x power, it would be very similar. Here's what the graph would look like. Notice that both functions pass through the point 0, 1. That's actually a really important thing to remember about exponential functions. The general form of an exponential function always has a point at 0, 1. Notice that both graphs also pass through the point 1, a, where a is the base of the exponential. So on 2 to the x power, we have 1, 2. And for 3 to the x power, we have 1, 3. That's another very important point to remember about exponentials. There will always be a point at 1, whatever the base is. Now, if you have a base that is between 0 and 1, the graph will look a little bit different. Consider y is equal to 1/2 to the x power. We still pass through the points 0, 1 and 1, a, which in this case is 1, 1/2, since 1/2 is the base. If you plug in larger values for x, we get smaller values for y. So if x is equal to 2, we will get 1/2 squared, which is 1 over 4. But if you plug in smaller values to this function, like negative 1, you actually start to get larger values. 1/2 to the negative first power is the same thing as 2 to the first power, which is just 2. If we plug in negative 2, we get 1/2 to the negative second power, which is the same thing as 2 squared, or 4. We can plot these points onto the graph. Connecting the dots in a smooth line, here is our function. Again, we still approach but never reach the x-axis, meaning we are asymptotic about the x-axis, or that the x-axis is an asymptote. Other functions with a base of 0 and 1 will look very similar. Here is what y is equal to 1/3 to the x power looks like. It still has the key points of 0, 1 and 1, a, but a is 1/3 in this case. So we really have two graph types depending on the value of the base. We have an increasing exponential function when the base is greater than 1, and we have a decreasing exponential function when the base is between 0 and 1. Consider y is equal to 1/4 to the x plus 1 power minus 3. This translation includes a vertical shift 3 units down, indicated by the negative 3, and a horizontal shift 1 unit left, not right, indicated by the x plus 1 in the exponent. If you've watched my videos, you know that I normally draw new axes that represent the horizontal and vertical shifts. The negative 3 indicates that we should shift the x-axis down 3 units. So this is what our new horizontal axis will look like after the translation. The plus 1 indicates that we should shift the y-axis left 1 unit. So this is what our new y-axis will look like. We have a new starting place, or like I like to say, a pretend origin at the point -1, -3. We normally have the point 0, 1 on our graph. Due to the vertical and horizontal shifts, we will not literally have the point 0, 1 on the graph, but we will have the point 0, 1 with respect to our new pretend origin, which is at the point -1, -3. So we will move up 1 unit from our pretend origin to find the point -1, -2, which will be on our new graph. We will also have an asymptote just like before, but it won't be the x-axis, it will be the new pretend x-axis at y is equal to -3. Typically, we also have the point 1, a on any exponential graph, which in this case would be 1, 1/4. We draw this point, not from the origin, but from our pretend origin of -1, -3. So if we move 1 unit to the right, and then 1/4 of a unit up, we'll have a new point on our graph. We know the general shape of an exponential with a base that is between 0 and 1 is decreasing, and we know that the asymptote is at the dotted line of y is equal to -3, so we can connect the dots in a curve to draw the graph. Note that we only have a horizontal asymptote, not a vertical asymptote, so we don't have to worry about crossing the vertical line at x is equal to -1. We only have to worry about not crossing the horizontal asymptote, which is at y is equal to -3. Let's try one more. We have -2 to the x power plus 1. In this case, we have a vertical shift 1 unit up, and a reflection across the x-axis, indicated by the negative sign on the 2. This will be a reflection across the pretend x-axis, as we have a shift up of 1 unit. Let's take care of the shift first. Everything needs to be shifted 1 unit up, so that we have 0, 1 as our new pretend origin, which means our asymptote will be at y is equal to 1. We normally would have the key points 0, 1 and 1, 2 on the graph of 2 to the x, but the negative sign tells us to multiply our y values by -1, giving us the new points 0, -1 and 1, -2. Now, these aren't actually points on our graph, but they are points that we can graph with respect to our new pretend origin. Starting at the pretend origin of 0, 1, we can move 1 unit down to get to the point equivalent to 0, -1 from the pretend origin, which is a point on our graph. Starting again at 0, 1, we can go 1 unit to the right and 2 units down to plot our second point. We know that y is equal to 1 is a horizontal asymptote, so we can draw the curve that connects the dots to complete our graph. Alright, my friends, that wraps up our video discussing graphing exponential functions.